Hello students, welcome to Vandukam. We are discussing electrochemistry, and in this video I will explain the most important topic of electrochemistry, that is Nernst equation. I will explain the derivation of Nernst equation. So before that, we should know why this Nernst equation is very important in this electrochemistry. And this equation is important because of mostly two reasons. First one is it will be helpful to find the cell potential or EMF of cell at any temperature other than 25 degrees centigrade or 298 Kelvin, which are the standard temperature, and also different concentration of the ionic solution other than that of unit concentration. This is also we have used in the standard condition to find out the standard cell EMF of the cell. And this calculation as well as solving of problems we have done in my previous videos, and if you want to watch those videos, you can refer to the description box for more detail of that. And the second point or the second important point for deriving Nernst equation is to solve many problems based on electrodes as well as cell. This is electrode potential or cell potential that I told you already. So we can find out the cell potential at any temperature and concentration by using this equation. Let us then start to derive this Nernst equation, and you please watch the derivation steps properly. Before deriving Nernst equation, we have to discuss the relationship between the Gibbs free energy and the cell potential. The cell potential or the EMF we are getting, that is utilized to do useful work, and this is known as your electrochemical energy conversion or spontaneous chemical reaction to give, or I'm just writing in a short, spontaneous chemical reaction to give your electrical energy from the galvanic cell, isn't it? We are talking about galvanic cell, and the total amount of electrical work involved in the cell is the product of your the charge and the voltage of the cell. Charge and the voltage or the potential or the EMF of the cell. We can write electrical work done, I'm writing below, is equal to electrical energy produced from the cell, I am just writing, and this can be obtained from quantity of electricity flowing into your cell potential or cell EMF. So this is electrical work done. So this quantity of electricity flowing can be calculated from the number of electrons which is involved in the cell reaction, and EMF would be your E. So for 1 mole of electrons that is transferred, 1 Faraday of electricity that is flows through the cell. So here if n electrons or n number of electrons is involved or n moles of electron is involved, that means the flow of electricity would be NF or NF Faraday. So we will get our electrical work done from the cell is NFE cell. This is your E cell is the EMF of or cell EMF. For a single electrode, the maximum work can be written as NFE, where E is the electrode potential. So let us first derive the electrode potential or the Nernst equation for electrode potential. From thermodynamics, we know that free energy term is associated with your work done, isn't it? from my last video, you can find about this free energy. If you have not watched, please go to the description for the detailed link of that free energy video. Okay, so free energy, so that means when free energy change is negative in a spontaneous process, then we will get maximum amount of work done by the system. So because this is negative, so delta G is equal to maximum work done, and we know that this minus delta G is equal to, or this would be your NFE in case of an electrode, or delta G is equal to minus NFE. And for standard free energy change, that is delta G naught, it would be NFE naught, where this E naught is equal to your standard electrode potential. Okay, let us consider a reaction for the electrode or single electrode potential, and by convention the electrode reaction is written with reduction in the forward direction. So let's just generalize Mn plus as a one metal which is reduced to M, and at the equilibrium constant K, as per the Le-Chatelier principle, this concentration of product by concentration of reactant. And we know there is one relationship between this equilibrium constant with the GIBBS free energy as well as
with the standard GIBBS free energy.
So in the last video we have discussed delta G is equal to delta G naught plus RT ln K. This is the equilibrium constant. Or by putting the value of K here in this equation, we have delta G is equal to delta G naught plus RT ln M by Mn plus, you know, where R is the gas constant. And in solution state, the concentration of solid
or the metal concentration is negligible and it is considered as 1.
So this equation becomes delta G naught plus RT ln 1 by Mn as RT ln Mn plus. So I have taken this one, so it becomes a minus and it went to your numerator. Okay, I'm just cleaning the above portion. So we know that delta G is equal to minus NFE.
Similarly, that of delta G naught is minus NFE naught.
Now substituting value of delta G and delta G naught in this equation, we have, I'm cleaning here so that I can write, minus NFE is equal to minus NFE naught minus RT ln. Hope you have understood this up to this. Now by dividing minus NF on both the sides, we have, so here also minus NF, here minus NF, here minus NF, we have to divide. So what we will get, E is equal to, this would be a plus E naught, this would be a plus RT by NF ln. Okay, let us convert this natural log into log. So we will have E is equal, when we will convert this natural log, we have to multiply 303. So RT by NF, this ln term becomes your log Mn plus. Now putting the values of R, F and T we have, so where R is equal to 8.314 joule per Kelvin per mole, F is equal to 96,500 coulomb per mole, and T we will take 298 Kelvin, that is 25 degrees centigrade. Then we have E is equal to E naught plus 0.0591 by n log mn plus. So this is the equation where we can find the electrode potential at any temperature and any concentration, ionic concentration, not in the standard state. We will use the standard electrode potential here and we can find out the electrode potential of that electrode. So this equation shows that this electrode potential depends on temperature as well as the concentration of the ionic species, where these are the constant term. Similarly, for the E cell, we can also find the equation E cell. It would be E naught cell plus 0.0591 by n log concentration of reactants divided by concentration of products. So, or else we can write E cell is equal to E naught cell minus 0.0591 by n log concentration of products by concentration of reactants. Here only plus and minus, where this would be interchange. So that you should remember. And if we will consider for this, for Daniell cell, E Daniell cell, if we will go through the equation, overall cell equation or the cell reaction, I am taking this one. This would be, I prefer this equation. So 0.0591 by n log copper ion concentration by zinc ion concentration.
Here n is equal to 2. Let's see
the overall cell reaction
of Daniell cell.
So as I told you, reactants, this is the concentration of reactants. So copper 2 plus, and this would be like this Zn. So here also copper concentration would be, because this is in solution, as I told, this solid, this is the solution state, so concentration of solids will be negligible. So for that reason only the ionic species or the solutions state, the ions are, concentration of ions are considered. So you can understand in a better way of this EMF of the cell and electrode potential when you will do some numericals based on these equations. So watch my next video for different numerical based on this Nernst equation. You can find the detailed notes of this derivation at the end. So keep watching, keep learning. Thank you.